So welcome back you guys to another video on cellular aspects of neurophysiology. Today we're going to continue on microscopes that are used in neurophys. So essential components of a typical light microscope. We covered this a little bit in the last video, but let's review. We need light sources. You know, it could be a little lamp or a laser or anything. An LED, it says. A field diaphragm, an aperture diaphragm, and lenses. You know, there's the 10x lens, the 40x, and the 100x. So telescopes for microscopes, right? So before microscopes, there were telescopes. And we kind of just used that same technology just to look inwards. So let's review two types of telescopes that we know of. There's the Keplerian telescope, which is defined as having two convex lenses. Notice how the focal point, there's a focal point there, okay? The focal point is in between those two lenses, which allows us to see a pretty good amount. Now let's look at the Galilean telescope, which is defined as having one convex lens and one concave lens. The concave lens serves as the ocular lens, or the eyepiece, while the convex lens serves as the objective. It's the convex lens. It's going to split it up a little more so that you can see more of it coming in. Right, and the focal point doesn't meet each other like it does in the Keplerian telescope. So let's talk about uniform illumination. You know, clear illumination, where the field diaphragm and the condenser diaphragm are adjusted so that the focal point between the field diagram and the collector and condenser lenses hits the condenser diaphragm. That's where the focal point is going to be. All right. Increased contrast. So DIC is going to be the differential interface contrast. It gives a 3D appearance to the sample. Alright, so notice how in this image we have two little light sources here. It's going to be one to each eye. Okay, so the Wollaston, I'm going to call it a Nomarsky prism. This is a Nomarsky prism. See how it has a little angular thing right there within this glass. It's a prism basically. So in the prism, one of the wedges is identical to the Wollaston wedge and has an optical axis oriented parallel to the surface of the prism. The second wedge of the prism is modified by cutting the crystal in such a manner that the optical axis is oriented obliquely with respect to the flat surface of the prism. This modification causes the light rays to come to a focal point outside the body of the prism. Okay? The focal point is going to be outside. Okay, the focal point is going to be outside. Together, the Wollaston and the Nomarsky prism increase the image contrast, giving it a 3D appearance. Alright? Just going to have to hard memorize that, buddy. Alright, now let's talk about fluorescence microscopy. Now, there's key components of the microscope that you should know that allow to select the excitation and emission wavelengths. It's going to be the dichroic mirror, right, and the excitation and emission filters. So let's go back to that graduate presentation that we saw. It's going to be sort of like a summary. You have this excitation filter right here in the beginning. Excitation filter. It's coming from a big light source. This is the sun apparently, but it could be an LED or whatever. So the excitation filter makes it blue, right? Okay, we have this blue light. It's hitting the dichroic mirror. It's a mirror, and that mirror reflects through the objective and onto the specimen. And then the specimen itself fluoresces. It gets excited and shoots up some light. Now that light goes back through the objective and through the dichroic mirror. This dichroic mirror, in this case, allows reflection from the excitation ray, and allows the fluorescence to just pass through, right? Kind of like a one-way mirror. And then that goes into the detector, and you're going to be able to see the specimen in pretty okay detail, right? Now, why does this happen? Why is the fluorescence different from the excitation? That's because the specimen absorbs some of the energy, scatters it around or something. It turns it into heat. It gets hot, and that heat makes the wavelength bigger because it loses energy. All right. So that's fluorescence microscopy for you, buddy. So there's another thing in fluorescence microscopy that you should know. So fluorescence microscopy, you're probably going to get this graph here. This graph, which looks like this, right? This part right here is the excitation emission. This part right here is the fluorescence emission. So this is the light going in, and this is the light going out. So what we want is a mirror right in between there that allows this light to pass through it and this light to get reflected by it. So we're going to need a mirror that has an excitation filter of 300 to, let's say, 420. Actually, or 400 is even better, 400. You still get a little bit of bleeding, but it's okay. 390 might be good too. Right? So for the other one, you're going to want 600 all the way to around, let's look at 460, 455. All right? And then the mirror you want right in the middle. So it's going to be 425. That'll be the best mirror ever. I mean, you're never going to get anything quite clear like that, right? But also you want the tips of these as much as possible. All right? The tips of these as much as possible. The tips are where you're going to see the most things. All right, so the dichroic mirror is in the middle. The excitation filters are going to be here and here. All right? And these are all going to be in nanometers. So you're going to get a question like this. You're going to be like, hey, what kind of filter do you use for this thing? Yeah, that's how your professor talks. Yeah, you're just going to pick something here for the excitation, something here for the emission, and something in the middle for the dichroic. Remember that you don't want the dichroic to really touch the excitation or the emission, and they can't overlap. You don't want some overlapping, or else you're not going to get a good image. That means that the excitation filter or the fluorescence, if the excitation is above the dichroic mirror, you're not going to see a good portion of what you're trying to look at, right? You're actually going to see a bit of the excitation come through that mirror, and you don't want that. You want that to be completely reflective. So let's go to some limitations. There's a few limitations, right? And that limitation could be that you can't see in 3D. Well, I guess the graduates didn't put down the limitation, but the limitation is that you can't see in 3D. It's going to be all 2D stuff. And we're in science, man. We want to get the best image possible, so we want to look at 3D. So you're not going to find that with fluorescence microscopy, at least in this kind of fluorescence microscopy. You're only going to find that in laser scanning microscopy, or LSM. Now, there's two types of laser scanning microscopy techniques. One is going to be the 2-photon, which is this one, and the confocal. So laser scanning microscopy techniques, or LSM. In this form of optical microscopy, light is scanned over the sample and the reflected intensity is displayed as a function of position to create a digital reflected light image of the sample. Scanning a focused laser beam allows the acquisition of digital images, so pixel by pixel by pixel by pixel. That's what digital imaging means, If you take a camera, like a phone or something, you take a picture, this one is around 16 megapixels, which means there's 16 million pixels making up an image. Alright? So one shot of that laser is 1 pixel. It's going to be one color. One color from that, not the image, but the specimen. Enough of those little points, enough of those pixels will make an image that you could see digitally. So scanning a focused laser beam allows the acquisition of digital images with very high resolution, since the resolution is determined by the position of the beam rather than the pixel size of the detector. Oh, pretty cool, right? So this includes confocal and 2-photon laser scanning microscopy techniques. Now, confocal laser scanning microscopy. It is a microscope system in which illuminating light is focused through a pinhole. Look at this, a pinhole aperture. And on the sample, the reflected light from that point on the specimen is focused to a point on the detector. For this reason, the microscope is confocal. So look at that, it goes through a pinhole, it goes through a pinhole. It's the focal plane, right? Now you're ignoring all the other light beams that are going all over the place. And you know what that gets you? Something that looks pretty cool. Let's look at this website called Microscopy U by Nikon. Very good company. I have a camera by them. I don't see anything. This is a wide field. This is what you get with a normal light microscope. This is a confocal microscope. Now look at that. You could see way better. Because now you're ignoring all this blurry stuff all around, things that are out of focus. You're ignoring out of focus light and only looking at the light that is in focus thanks to the pinhole aperture. This right here is out of focus light. This one thing right here, that's focused light. So if we change the focus, we start looking at different parts. This part right here, gone when we go to this. See how cool that is? Now if we slow down the scan line, you're probably going to get a better image. If you speed it up, it's not going to look as good, but you can still see it. Alright, so magnification 60x, yeah. Good stuff, right? This is the medulla oblongata, part of the brain. Now let's look at two photon laser scanning microscope. The phenomenon of a photon excitation arises from the simultaneous absorption of two photons in a single quantized event. So knowing two photons, you know where everything is, and you can basically, you don't need the pinhole aperture anymore, because now you know where everything is. So since the energy of a photon is inversely proportional to its wavelength, the two absorbed photons must have a wavelength about twice that required for one photon excitation. So for example, a fluorophore that normally absorbs ultraviolet light at a wavelength of around 350 nanometers can also be excited by two photons of NIR light at around 700 nanometers if both of them reach the fluorophore at the same time. Alright? Now this is what it looks like when you do two-photon microscopy with calcium ion imaging and the two-indicator method. Pretty cool, right? Well, that's it for today, guys. See you next time.